the cloud. There we go. Okay. What's that? Okay. Yeah.
Just a quick question. How long are you opening?
Indefinitely.
Oh, okay.
But you need to get it done. So yeah, not wait till the end of the semester. The whole point of that is that you guys are up to speed by the end of let's just say a week here. I'm gonna be willing. If you don't get a 70%, you're gonna need to come in and see me, and I'm gonna work one-on-one with you until we get 70%. It's that important. I want everybody here to get 70%. So, okay. So equilibrium. In general, the definition I like to use is a situation in which there is no tendency for change. A situation in which there's no tendency for change. We kind of got, we're at that equilibrium point, right? Until something rocks our world, we feel good, we're happy, we're whatever. A situation in which there's no tendency for change. When we apply that to supply and demand, we come up with equilibrium price and equilibrium quantity. So specifically in our graphs and what we've been doing, that little P star where the two lines cross for supply and demand, equilibrium price is the price in which the quantity demanded, the amount of stuff that people want to buy, equals the quantity supplied. And we saw that with our schedule goggles on, right, where the two numbers were equal, where the two lines crossed. It was where quantity demanded equals quantity supplied. And equilibrium quantity, Q star, is a quantity where quantity demanded equals quantity supplied. In other words, they're all kind of three, and rather than replicating it, we just say Q star, and they're all three equal to each other. All right. So we worked through some examples. You're going to have homework problems and some other things on shifting the curve. That's really all Chapter 3 material. Today we move into Chapter 4 on elasticities. So Chapter 4 is the elasticity of demand. So this week we're hitting Chapters 3, 4, and 5, which sounds like a lot of content, and it is to some degree. This is the only week where we'll have 3 chapters. But they're all very related to each other. They're all talking about supply and demand. All 3 are really touching on similar topics. And so with the elasticity of demand, we're going to start to quantify changes. Do you remember last time when I somewhat tricked you and I said what was happening when both curves shift, and the right answer was we don't know, and because we just didn't have enough information. And so the reason that economists get paid 6 figures is to give good information, good quantitative detail. And so if you've got a consulting gig for a company, let's say I guess Pepsi comes to mind for some reason, and I think her name is Indura, is the CEO of Pepsi. She hires you on, and she says, well, I'm just curious, if we drop price by 10%, you know, what's going to be the impact? And you go back, and a week later you come back with the detail, and you say, well, if you drop price 10%, quantity's going to go up. The quantity that you sell is going to go up. Is she going to be cutting you that consulting check for $10,000 for that information? No, she's going to boot you right out and say, give me the details, right? So Chapter 3, we have a more qualitative analysis. As price goes down, quantity goes up, right? As price goes up, quantity goes down. We talked about the price of substitutes, price of complements, normal good, inferior good, and so we're talking about directional changes, what I call qualitative changes in variables. And so now we're going to get a little more meat on the bones here with elasticity and actually calculate some quantitative effects. And so the elasticity of demand, I'm going to use the notation here, a little summation sign, sigma subscript d. And the elasticity of demand is a number that shows the responsiveness of quantity demanded to a given change in price. A number that shows the responsiveness of quantity demanded to a given change in price. We're going to throw our equation goggles on right away today. That number is the ratio of the percentage change in quantity demanded over the percentage change in price. The percent, so my notation here is the triangle remembers change. Percentage change in quantity demanded divided by the percentage change in price. So we're going to take one divided by the other. All right. Who remembers percentage changes? Maybe from some math classes, or you macro people. We went over this quite a bit then. What did we do for a percentage change in some variable x? Is equal to what's that? Final minus initial, new versus old. Okay. Divided by the total quantity? No. Divided by the old. Yeah. So new I mean, that's the general theory is the new number minus the old number, the old number divided by the old number. And that's how we did it in macro class when we calculated inflation. Those of you who are going to be taking macro later, we'll do some percentage changes. This is the normal way that it's calculated. And to screw you up a little bit here, that's not the way we do it here. And we do it for a good reason, I think. I'd like to think, anyway. If we take the demand curve, and I look at a change of $10 from 100 units, and let's just say we do a $11 and it falls to 80 units. Okay, so we'll take point A and point B on a regular old demand curve. You can see what we're trying to do is put some numbers to this law of demand business, but now we're going to see how much the changes are. Using this formula, how much did I increase price by? 1, I increased it by $1, but in percentage terms, 10%, right? New minus old, 11 minus 10 divided by 10 gives me a tenth. 1 divided by 10 equals 0.1. Slide the decimal place over a couple spots, 10%, right? So that was a 10% change in price. Now, if I did just the opposite and I cut the price by $1, I'm starting here and I cut the price by $1. Am I going to get back to 10? If I do a 10% reduction?
No.
No, because now I'm going to get the new number is 10 minus the old number divided by the old number. 1 divided by 11 does not equal 1 divided by 10. Right? So a increase of 10% is not the same as a 10% decrease using that formula. The the number of the change in value is the same, the dollar.
It's 10% of $11.
Right. But the number that we're getting at the end of the day is something different, right? So this $1 price change using this formula is 1/11. So it's going to be something less than a 10% change. So we're going to want to correct for that. Now, notice what is causing the problem here with an increase versus a decrease. What's causing the problem? The numerator or the denominator? The denominator. The downstairs is the issue, right? So here's our correction we're going to do. We're going to divide it by the average of these two and just call it $10.50, $10.50. And now an increase and a decrease will be treated the same way. So that's going to be our technique over here for using or calculating elasticities. It's called the ARC method for calculating the percentage changes. And so we're going to have the change in quantity over the average quantity divided by the change in price over the average price. And then just to be super complete here, we're going to take the change in quantity is the new quantity minus the old quantity divided by the average, which is the new plus the old divided by 2, right, or half of that amount. So there's your average. And then we're going to divide that by the new price minus the old price divided by the average price, which is the new plus the old divided by 2. That sucker's that sucker. It just kind of all maps out. All right, so let's put this thing to work here. Let's do an example where we've got a downward sloping demand curve. We'll look at $12 and $10, 2 points on this demand curve. And we'll go from 100 to 140. And we'll move from point A to point B. So calculate the elasticity of demand using this formula and those numbers. Here's how a question would be worded. Suppose there is a price decrease from $12 to $10. What is the elasticity of demand? So you can work with your neighbor, pull out your calculators, you can pull out your phone if you put it on airplane mode for me so that you're for sure not being disrupted other than your little calculator on there. That would be fine. We're going to be burning up some numbers here. So I'll walk around the room and help you out. Calculate the elasticity of demand using this information. So yeah, good first step is getting the new number and the old number mapped out. The 12 and the 10, you might want to just on the side of your paper, right? P-N, or you can use P1 and P2 if you want. You'll see that on your homework exercise, P1 and P2.
Oh, wait. Negative 40.
I would start with write down and rewrite the
Actually, do this stuff.
the percentage change you want to do. Write that and then just all of the down. Oh, you're doing the. So make sure you draw
This is
the.
easy, bro.
Yeah.
Check this out.
First part is just to set up the problem. You guys should have on your papers copied down basically what I have here for starters. So make sure you got this and this on your paper, and then maybe the question if you want.
So 140 minus 100 over 240.
Okay. All right, so start with that formula. So you can just look on the board there. So and actually I would go ahead and draw the graph. Or did you on the other page? Oh, okay. Oh, that's the old one. I erased it. So yeah, draw this graph. So start by drawing the graph that I have drawn there, the 12, the 10, the A, and B, and all that jazz. 5.4, okay. 0.5. You know what? I have like this. I'm relying on you guys. Your setup. Okay, so here's one thing that you messed up. And that's why I said, map out your
It would be 10 minus 12.
which one's the original two that we have erased?
Right here,
Yeah.
divided by price per new.
Yeah, let's see if yeah, so now you got to map out that 12 corresponds to which one's the new one? Which one's the new one? Yeah, but show it. I want to see it. So map out your P1 and Q1. You want to use the new and the old, whatever. Yeah, sure. Okay, good. Which one now? Which one's over? Yeah, good. Yep, that's what you want to do. It's important that you map out which one's the new ones and which one's the old one for the quantity and the price. I think I'd like to see a little more work so I can tell if you're right or not. I got that. Where's your? This is it? Yeah. Is that a minus sign one?
Yeah, it's
Supposed to be.
Yeah.
Yeah. No, you're on the right. You're on the right track. Yeah.
Well, we ended with 1.
But now you got to get a final number for me. What is that number? That's the right thing for the downstairs, which is missing the upstairs. So make sure you got the, first of all, this is the new number, right? So let me see it. Let's just call this P1. P1 corresponds with Q1. P2 corresponds with Q2. Right? And that's the new.
Oh, wait. 140 in my new.
You did this okay here, but you missed the top line.
Yeah.
So the elasticity of demand, rewrite everything I got there. You can jump to the blue one if you want. The setup looks good. I haven't calculated the answer yet, so I'm going to start. So part of what I'm telling some of you is to make sure you got your P's and Q's set. Is that if we call this P new, if you want, or P1, you'll see in the textbook. I'm sorry, this is not the new, that's the original. Get you guys screwed up right away here. So the original, and this is the new one, right? Now this new one corresponds with this one, so this is then Qn, or Q2. And this one corresponds with here, so this is Q0. And then you got to have that set up here. Why is that important? What's it going to kick out for you? As you calculate your number, why does that end up being pretty important? It's from one price to the next, yes, but from the number that you calculate, what's it going to kick out for you for this overall expression? Fraction, yes. Decimal, possibly. No, who said that? That was the right answer. I just heard it. A negative number, that's right. So the elasticity of demand is going to be a negative number because demand is downward sloping. Price goes up, quantity goes down. If price goes down, quantity goes up. So that relationship is always a negative number. If this upstairs goes up, this goes down, they move in opposite directions, you're always going to get a negative number there. So that's why that's important to link up. All right, so what do we got for answers? Let's have a little round robin here. Negative 6%. Negative 11. Negative 3.4. What else? I saw some other numbers. No, be brave. Who cares? How much? Negative 1.83. Anything else? Which one's right? Which one did you guys get? Are you not there yet? You need a little more time. 1.83. How many people had 1.83? Oh, that's looking like majority might be in the right ballpark here. I have not calculated the answer to this, so I need your help, but I'll work on it with you together now. So if we got change in quantity, and this is the new and this is the old, I got 140 minus 100, right? 140 minus 100 is 40. The average of the two is 120. Divided by the difference in the prices. New is 10, so 10 minus 12 is negative 2. The average is 11. And then it's just burning up the calculator. This thing minus this thing, we can flip them around and do a little gyrations, but we get this is equal to my 1.83 people. Is this looking right for you?
Yes, sir.
All right, then let's call it good. All right, piece of cake, right? Not yet. We're going to get more practice on it. We're going to get more practice on it. Yeah, question. Yes.
I get that, but technically, no matter how you know which way the graph is going to go, I'm going to automatically increase the right answer. I did the opposite way, but
You mean you switched them around? Yeah, that's why we did it that way. So if I'm understanding your question right, if you did 100 minus 140, and then it's 12 minus 10 down here, you will get the same answer. That's why we set it up with the averages. So yeah, you're right. You're fine, as long as you remember that the negative thing. And
I got negative 6 because I completely flipped the equations.
you flipped all these around, yeah. So you gotta be careful of just making sure you're consistent. So you need to have this formula memorized. Now, I also want to tell you that it's equally important for a lot of your homework and test questions to have this memorized. Some problems we do, they might give you the percentages rather than the numbers, and you won't have to burn up the calculator like we did with this problem. It'll just say, suppose price goes up by 10%. What happened, and quantity falls by 22%. What's the elasticity of demand? So you have to know this one also, in addition to burning up the calculator with that. All right, so any other questions on the mechanics of it? Yeah. I will later. Okay, so here's your challenge question. Point C is at 8 and 180. Straight line demand curve, rise over run. What is the elasticity of demand going from here to here now? Another price decrease from 10 to 8. Quick answer or not? If we go from, let's call this now 1 to 2 to now P3. So now we go from 10 to 8. And we're going from 140 to 80. 1.83? Straight line demand curve? Okay, just for practice, do it. Go through the gyrations. Go through the gyrations. Trust me on this. You need to go through the gyrations. So this will be good practice for those of you who are still shaky on the first one. Okay, now those of you who are having a little difficult time the first go around, let me come around and get you set straight up. I heard you kind of say yes. How you doing?
We just messed up the.
Oh,
We just
okay.
put a negative there, so we
Oh,
got
that
the
wasn't
positive.
good.
Yeah,
So you
that's
figured it
right.
out. Okay. As soon as somebody gets an answer, shout it out.
Shout.
Gosh, you know Nudge? Okay, so I want you to prove it. Calculate it out. Trust me. Trust me. You're not doing it right if you think that's correct. Yep, good. I want you to prove it to yourself. If you got negative 1.83, you did it wrong.
Negative 5.5.
1 point what? 125 I got. I thought I heard a 1.5 too, or I saw a 1.5. So let me just jot these down.
I got 0.6.
1.25. Thought I saw somebody else who had a 1.5. Negative 1.125. That was you, so let me correct that. Negative 1.125.
I got a negative 0.6.
Negative 0.6.
Negative 0.5625.
Negative 0.5625. I think I heard you say negative.
Divided by 320.
Okay, Davis, Tyler, what's up? Let me see your papers.
I'm still trying to get the number.
So Tyler, I didn't quite see I don't see your calculations, Davis. Are you guys sleeping on me or what? I'm going to always ask you to prove it up, so be ready. You guys got to be going.
I said I did it on my phone. You can hear me. Sorry.
1.13.
Yeah.
Okay. Was that a negative or a positive?
Negative.
Okay, good. Okay. All right, so let's set this one up then. We've got, here's some of our answers. I've got elasticity of demand, change in one over the change in the other. It technically doesn't matter what the new and the old was, like we pointed out before. So now if I go 180 minus 40 gives me still 40, but the average is what's getting us, right, is now 160. And then we've got 10 minus 8 is 2, a $2 price change, just like before. That's the slope part kicking in. But now, of course, our average is 9. And then that's still negative. And so which one's right up here?
1.125.
1.13, 1.25, maybe some rounding here, right? Okay, so I can buy these two equal together. So negative 1.125. Show of hands, how many people got that? Okay, so it looks like majority's probably right. I'm not doing these calculations myself here. Question? Sure, some of the rounding. Yep.
160. You said that's 160, or did you change that to 180?
So what we're really doing, this is 180. Oh, did you use 160?
Yeah.
I originally wrote that. That's what screwed you up.
Oh,
Okay.
all right.
Sorry about that. All right, so graphically, since we're using the averages, this is how you should show it graphically. We're centering it on the average, so you can kind of think about the elasticity of demand here as 1.83 in absolute value. I haven't told you about this little tricky thing we do. And then over here, it's centered on 9 and 160, and the absolute value of the elasticity equals 1.125, let's call it 1.3. So the elasticity of demand changes on us, even with a linear demand curve, because it changes depending on where we're at. Why? Does anybody see why? It's not very easy to see. So I'll be impressed if some of you can tell me why.
We're coming to that equilibrium.
Nope, has nothing to do with equilibrium, because I don't have a supply curve on here. So it just has to do with kind of the raw calculations. If I do a $1 price change up here, like really high up here, if I do a $1 price change, in fact, let me just change it on you. Let me go away from this example slightly just to make it obnoxious. If I have a $100 item, give me a good $100 item. Phone, kind of a mid-range phone or maybe used phone. All right, so I got a $100 cell phone. If I increase the price by $1, roughly, not worrying about the average stuff, roughly what percentage increase is that? 1%, right? So $100, a $1 increase would be a 1% increase. Now, if instead I have a $2 or a $1 item and I increase it by $1, what percentage change in price did I just have? 100%, right? Same dollar, but it depends on where I'm at on the curve. If I'm at this end of the range, the percentage changes in prices are going to be really, really small, making this number get really, really big, right? And that's what we see happening here. I had these numbers pretty tight, but the number's increasing, right? In absolute value, it's increasing in magnitude. And at low prices, I have big percentage changes. I also have very small quantity changes. Same things going on here. In percentage terms, I've got a small quantity change making this real small relative to this. So everywhere along a linear demand curve, every point that you evaluate, you're going to get a different number. And that number is going to range between 0 and infinity. That's the range of elasticities along a linear demand curve. All right, so key points. Key points here. The elasticity of demand, I'll just put the absolute value signs there. Everybody comfortable with the absolute value? We just kind of strip out the negative sign. I didn't really tell that story of why we do that. We do that because, well, everybody knows it's negative. Everybody knows the law of demand. So let's just talk about it as a positive. And literally, it's kind of like we verbally talk about it as a positive. Whenever I write it on paper, i.e. when you write it on your exam paper, I want you to be careful with that. So the elasticity of demand equaling negative 1.83 can also be rewritten mathematically as 1.83. Everybody knows this switch. On your test, if you give me this, elasticity of demand equals 1.83, that's wrong. Now, I'll probably give you some partial credit. I'm not that harsh, but that's wrong, right? So remember that that negative sign is important as we plow through some of the problems that we do and maintain consistency here with the absolute value business. So the elasticity of demand is different along different points of a linear demand curve. And in fact, those values are greater than 0 and less than positive infinity. The absolute value of the elasticity will range between 0 and infinity.
So should we always place our answers like that?
One way or the other. I'll accept them both. I'll accept them both,
Okay.
as long as it's formatted right. If you don't have the brackets over it, then it should be a negative number. Okay. How about interpretation? When you go to the CEO of Pepsi and you tell her, well, the elasticity of demand was calculated to be 1.83. She's going to say, I'm paying you $10,000 to tell me what that means. So, what does it mean if we have the elasticity of demand equal to negative 1.83? Anybody want to take a stab? How would you explain that to the CEO of Pepsi, what that number means? Yeah?
Possibly the difference in sales.
We're going to tie it back to sales, but I want to be very specific. She's paying me $10,000 for this analysis. By the way, it'd probably be a lot more than $10,000, but I'm just pulling a number out of thin air here.
How much product will be demanded if she changes the price?
Yes, but now more specific. You're right. You're tying the right things together. If you look at this definition, a number that shows the responsiveness of quantity demanded to a given price change, that number turned out to be 1.83. Oh, and by the way, is that 1.83? We kind of got lost in things here. Is that was that dollars or percent, or was it units of Pepsi or something, or percent, kilograms?
Maybe percent.
Percent. Unitless. It's a nothing number. It's a unitless number. I know that sounds weird, but since it's the ratio of two percentages, the percentages kind of cancel out if you were doing the math in a sense. So the percentages kind of disappear. It's a ratio. So on your definition, if you want to go back, I don't like to confuse that early on, but maybe add, it's a unitless number. That always seems to be a good test question or homework problem. A unitless number. Not meaningless, because that's what we're going to do here. Not meaningless, but unitless. So the meaning becomes a little bit easier if you have memorized, like I told you to do, this formula. If you write this right next to the number, the interpretation starts to pop out at you. There's one more trick to do. How can you turn any number into a fraction? Put it over 1, right? Any number can be turned into a fraction real easy. Put it over 1. Now look at what's going on. Now all of a sudden we've got almost a sentence building here, right? A 1% increase in price will lead to a 1.83% decrease in quantity demanded. Let's write that out. So the interpretation is a 1% increase in price will lead to a 1.83% decrease in quantity demanded. Now, you might also number of sales, number of units sold. So your textbook might say sales or number of units sold. That's what we're really looking at. That percentage falling by 1.83%. Now the CEO of Pepsi's like, oh, okay, that's why I paid you $10,000, right? Because now it's very specific for her to be able to make some decisions at their company with, should we do a 3% change? Should we do a 2% change? Should we not change it at all? Is that a big enough bang for our buck? Are we going to tick off our customers by raising it 1% if this is all we're getting? If this number, you know, was something less, maybe I'd consider it, right? All of a sudden we got meat on the bones for the profit maximizer to think about.
I think eventually the absolute value will be less.
The absolute value business is strictly for verbalizing and having a conversation. So when I go up to talk about it, I might say, oh yeah, we came up with an elasticity of 1.83. In other words, we don't say negative 1.83 typically, and so that's the way we verbalize it a lot. It also is kind of nice here when we start talking about, is the elasticity number getting bigger or smaller as we move along here? Well, the responsiveness, is that getting bigger or smaller? Think about it in terms of responsiveness. As this number grows, as I move this direction, are consumers becoming more responsive or less? More. If we talk about, you know, the negative number business, is this negative number technically bigger or smaller than this negative number? Which one's bigger? Technically this one, right? Because of it being negative. So that's another reason why we talk about an absolute value, because we're really interested in the kind of the magnitude, the effect that we get. And so a bigger number means a bigger responsiveness, a bigger change in quantity demanded.
Where did you get the 1% increase?
So, good question. Yeah, so the 1% I kind of made up in order to facilitate the interpretation. So the formula's right here, right? This is what I started off with. And so in order to tell this story nicely, if I remember that formula and I know that the elasticity is negative 1.83, I can put any number over 1, and now a 1% increase in price leads to a 1.83% decrease. Okay, yeah?
So if you put it over 2, you have to double the 1.83.
Yes, yep. Another common thing we might do is if you wanted to talk about a 10% increase. I like 1 because we're usually talking about small changes. What's true for 1% isn't true for 100%, right? So if I say, suppose I double my prices, am I going to get 183% movement? Maybe not. You know, that's too far. For economic analysis, we like to look at single unit changes, kind of small changes. In fact, when we get into higher levels of economics, we might even throw some calculus at it, and we're going to have an infinitesimal change, right? So really small, we like to kind of focus in on small changes. So, but if I do this, maybe don't draw this on your paper. If I do this, what do I got to do up here? Multiply by the top by 10, or simply just shift that over. Now a 10% increase in price leads to 18.3% decrease, right? So it works. So up to 10% I'd be comfortable, or 2%, like you say. Yeah, it's a ratio, so you think of it that way. Okay, good. Any other questions? All right, so that gets us that gets our beak wet here for elasticities. Now we're going to do some extreme econ with a couple extreme cases of elasticities. All right, here we go. Hang on tight. You know, we got extreme sports, and you know, you got those snowmobilers that are jumping 100 foot over the jumps. Well, this is some extreme econ, so hang on tight. We got 2 cases here, 2 kind of special extreme cases where we've got a demand curve that's potentially flat and another demand curve that's perfectly vertical. And so I want to think about the elasticities here. we can kind of go back to picking 2 points of the A and the B just like we did before. And so we got, oh, okay, I get it. We've got a Q1 and a Q2, but P1 is equal to P2. So that makes it kind of special case. If I drop down to my formula that I am working on memorizing, I've got the percentage change in quantity demanded over the percentage change in price. And so just keeping things a little generic here, I've got a Q1 and a Q2, so that's just going to turn out to be some number. Some number divided by no change in price, that'd be a 0. Some number divided by 0 equals 0. Okay. I see some people fidgeting on that one. Why? I saw you kind of do a little tweak or twerch or something there. What's that?
It's an indefinite number divided by 0.
Ah, so you remember back to that 5th grade teacher, right, that said, wait a second, Sonny, you can't divide by 0, right? That's just like illegal or against some sort of math rules or whatever, right? So this was undefined, I think, back in 5th grade math. Maybe you can't divide by 0. But now you guys are in college, so you're going to outsmart that old 5th grade teacher. Mine was Mrs. Von Berg, who we affectionately call Mrs. Von Bag. But that was 5th grade. I don't do that kind of stuff anymore. So, all right. So what I want to do here is kind of use some a little bit tricky thing. Is like, okay, Mrs. Von Berg, I can't divide by 0, but I'm going to divide by something really, really close to 0. So how about 1 over 1 million? Now, that's 1/1,000th, right? I mean, on the number line, I'm getting really, really close to 0. I'm not there, but I'm getting really, really close to 0. And I can see some of you math people that are like, well, Russ, that's just not close enough to 0. You got to get way closer. Come on. And so we're like, okay, well, why don't you, how about 1 over 1 billion? Nope, not close enough. How about 1 over 1 trillion, right? So now we're at a trillion. And if you don't like that number personally, get a little closer. You get as close as you want. Get as close as you want to 0. Now, as I start to look at these numbers and get closer and closer to 0, what happens to this overall expression? Gets really, really small. How do I divide some number divided by a fraction? What's the process to solve that? Flip the denominator and multiply it times the numerator. So some number divided by 1/1,000,000th is all of a sudden 1 million times that number, 1 billion times that number, 1 trillion times that number, or as small as you want this number to be makes this whole thing blow up. And what do we call that in math class? What do we say when something is getting as big as you can make it, or as big as it? An infinity. Good. All right. So that is maybe the only dose of calculus some of you will get at Auto University. But you just took the limit of this expression as this little downstairs approached 0, and that makes the whole thing blow up. So the elasticity of demand for a demand curve that's perfectly elastic is infinity. And so we say that this is a perfectly elastic demand curve. The elasticity of demand in absolute value is positive infinity. Without the brackets, it'd be negative infinity. Perfectly elastic demand. Let's do the same exercise over here. Now we've got some P1 and we've got some P2. And we've got a Q1 equal to Q2. And what are we going to get when we do this one? Now we're going to get our 0, right? So we get the percentage change in quantity demanded divided by the percentage change in price. For price now I get some number downstairs. Upstairs I get 0. The 5th grade teacher would even allow you to do this now. 0 divided by any number is 0. So the elasticity of demand is equal to 0. And this demand curve is perfectly inelastic. Well, we don't need to put the brackets on there, but just to be consistent, 0 is always 0. All right. Questions there at all? Now, notice something. What we did is we kind of completed the circle, right? We had equal to infinity, equal to 0. The one that we started off with, and actually I'm going to take this opportunity to do my favorite graph in economics here. So we're going to draw 2 graphs stacked on top of each other. The one that was downward sloping ranged from infinity. As you approach the vertical axis, it got close to infinity, but it never got there, if you can say such a thing, right? So it was a calculable number. The closer we got up here, got down to 0 here. Now, somewhere in the middle it equals 1, and that ends up being a special place for us. So where that happens, it's just kind of a mathematical oddity here. If you draw a downward sloping demand curve, I don't care how steep it is, and you bisect this at the midpoint, take approximately the middle, go straight up, and identify that point, that is where the elasticity of demand is equal to 1. And we call it unitary elastic. If elasticity of demand is equal to 1, what's happening with this equation? What's true about the numbers here? Percentage change of this and percentage change of this? They're the same, right? Not that there's no change, but they're the same, right? So if this is 11%, this is 11%. If this is 8, this is 8. So we're just saying that that expression ends up being equal to 1. All right. This direction, numbers are getting bigger, so the elasticity of demand over this range is greater than 1. This is unitary, yeah, equal to 1. At this point, demand is said to be unitary elastic. On this range of the demand curve, the numbers are all bigger than 1. If they're bigger than 1, is that showing a greater responsiveness by consumers, or are consumers kind of unresponsive to price changes? Greater response, right? Now check out, I know that not everybody's comfortable at looking at equations and interpreting, but if this expression is greater than 1, the upstairs is bigger than the downstairs, right? And so a 1% increase in price leads to a greater than 1% increase in quantity. So people are really responding to it, right? And that's what the 1.83 is showing. The percentage change in quantity is greater than the percentage change in price. And so this is the relatively elastic demand region of the demand curve. So demand is said to be relatively elastic, or the elastic range of the demand curve. The elastic range of the demand curve. Of course, down here, all the numbers are less than 1 in absolute value. Coming back to our equation, in order to get a number here that's less than 1, like 0.5, let's say, right? If it's 0.5, then let's say there's a 10% change in quantity and from a 20% change in price, right? 10 over 20. You bumped up price 20%, or let's say decreased it. You cut price 20% and only sold 10% more product, right? You're like, what the heck, man? That was a great sale. I should have sold a lot more. Consumers are relatively unresponsive to that price change. So they are relatively inelastic. So this is the relatively inelastic range. So if you want, got to be a little bit careful here, but as we approach this axis, the horizontal axis, remember that the number's getting kind of close to 0. So it's going to 0. And up here, the elasticity of demand is approaching infinity. So that number's always continually changing along there, just like we showed with the numbers we calculated. Okay. Whew. Now we are rolling. Questions? Hitting you with a lot. We're gonna pace ourselves here after this. I'm gonna get to a little simpler stuff since we're burning up the brain. Sam?
Is the price drop from the relatively elastic range to the relatively inelastic range? They would sort of respond to that a bit.
Are you talking about doing something like this from this point to this point?
Yeah.
So the way we calculate the formula, it's going to be centered on the averages. So it would depend on where it fell, right? So you'd actually fall, if you were a little bit more weighted up here, you'd fall to this side. If you were a little more weighted to this side, you'd fall down there. Dirk?
In the case of perfectly elastic and perfectly inelastic, what does that mean as far as like demand? Like, do people just not care?
Yeah, so that's probably good a time as any to soften things up, back to the economics of it. So what types of goods, let's try to put some real reality back into this. What types of goods might look like this, where, boy, it doesn't seem to matter what you do with price, people buy the same amount? Gas. Good. So gas is relatively inelastic. It's not perfect, by the way, but you get the idea, right? So they're under gas. What else? Water? There's some. You're right. I think it's a lower elasticity, but we might have so the thing with water. The reason I hesitate a little bit is if water prices shoot up, what else do you drink? Beer, which of course some of these have water, so this might not be the best example, but soda, milk, whatever. We can substitute. If gas prices go up, what's your substitute? What else can you use? If you want to use your car, nothing basically, right? But there are some substitutes that we do observe in the real world. What do you do with transportation? The good is transportation. Gas prices go up. How do you get to school? How do you get to work? Bicycle, a good old-fashioned way. The train, the subway, whatever. There's other walking. Oh my gosh, there's an idea, right? We could walk for life. How many people are walk for life in the morning here? Walking early morning? Got to have some walkers, I'm guessing, right? That's a great class. Walk for life. So we can find alternatives, but those aren't very good substitutes for our car. And so we tend to be pretty inelastic. How about cocaine? How many cocaine users we got? So what do you find when price goes up for cocaine? Do you buy the same amount or do you cut back? Right? Heroin. How many heroin addicts we got? Right? Heroin goes up. You still need your juice, right? How many people know some meth addicts in their world, right? There's meth is kind of a problem in different places. So drugs tend to be pretty inelastic. If that's your thing and you don't have alternative substitutes to getting high that are relatively cheaper, then you might be stuck with it. I think that's where the heroin stuff is. They can't quite get the same high from other stuff. Okay. So that's the idea here. When we, since we got on that topic, I'll come back to this graph in a second here. So let's see. How about this? Here's a good test question for you. Which demand is less elastic? Question mark. Which demand curve is less elastic? Demand curve A, situation B. B, I hear. So now I'm tweaking with the slope. Which one, how many people say, everybody caught up? I just want to make sure everybody's looking here. We can have an equal vote. How many people say A? How many people say B? Woo, okay, vast majority. So we're doing good here. We're getting the picture, right? So as this thing starts to get steeper and steeper, one of the little tricks I have that I'll pass along to you, I try to do that every time I can, it starts to look more and more like an I, or inelastic, or less elastic. So the steeper a curve gets, the more inelastic we say it is. Now, this rule, where is it? This rule still applies no matter what the steepness is. As long as there's some slope and we're not falling into one of the extremes, this always holds. So in other words, if I take this steep one, bisect it, and then go up, it's unitary elastic right here. You can see I'm kind of off the screen, right? And there's still a elastic range right up here, all the way up to there. So just because it's steep doesn't mean it loses these properties. But over the relevant ranges, so to speak, of the demand curve, all of this is pretty much the market. It's mostly all inelastic, right? Because of its shape. Similarly here, here's the demand curve. We'll draw a lot of these. You'll see some on your homework where we just draw a demand curve like this. Well, this demand curve actually extends out to here. And there's the midpoint right here. Go up, and that's where the elasticity of demand is unitary. But again, over all relevant ranges of the demand curve, the area that we're looking at, they're probably all greater than 1. They're all relatively elastic. Okay. I'm going to give you the last summary, and then we're going to move on to some other related material to elasticities. So summary. And this is going to be a little equation goggle-ish. So if the elasticity of demand in absolute value is greater than 1, demand is relatively elastic. And from our formula, it means that the percentage change in quantity demanded is greater than the percentage change in price. This is helpful if there's a kind of a word problem on a multiple choice or something else. They might give you kind of some of those details. If you kind of remember some of these pieces, if you've got the formula memorized, that's where this is all going to help. So greater than 1, demand is relatively elastic. That means the upstairs is bigger than the downstairs. If the elasticity of demand is equal to 1, we have unitary elastic. And that means that these two animals are equal to each other. The percentage changes are equal. If it is less than 1, then demand is relatively inelastic, and the upstairs is less than the downstairs. And that's just purely cranking out the math and looking at the formula and thinking about these different cases.
What's that bottom part say?
This one here?
Yeah.
That's relatively inelastic. I kind of abbreviated. Demand is relatively inelastic. And the percentage change in quantity is less than the percentage change in price. Oh crap, I just erased our next topic. I wanted to come back to that. That's all right, maybe it's good we can always redraw. Okay, any last follow-up? Get that all down on your notes? I want to redraw the graph I had up that I erased, where I was going to stack, so you guys wouldn't necessarily have to redraw this. You could just use the one you had. Midpoint, unitary elastic, elastic range, or inelastic range, and elastic range. Okay, the same picture that we were doing before. This is the demand curve, price and quantity. Downstairs, I'm going to measure total revenue for the company. We talked about total revenue a while back. We're going to spend a lot of time on it when we get to chapters 10, 11, 12. That's a ways off yet. What was total revenue? Formula, equation goggle? It was a simple one, but little equation goggle for total revenue. Total money in the cash register.
Yeah, profit minus cost.
Profit minus cost was the profit. So you're maybe saying some words wrong there. The profit equation was total revenue minus total cost. What is total revenue? How did we calculate total revenue?
Price times quantity.
Price times quantity, that's right. So just price times quantity. If I had 100 units and they were at $3 a piece, 3 times 100 gives me $300 in the cash register, right? So this is price times quantity. So over here, I want you to draw the formula out. Total revenue is equal to price times quantity. Notice that this is an interaction of this and this. The reason I have them stacked is if this happened to be 1,000 units, then come straight down, this is 1,000 units. In other words, we're measuring quantity in the same magnitude in the downstairs graph as we were upstairs. Now, if I price it at exactly this point, if my price is that point, what's my total revenue? 0, right? It's too high. Price is too high. That's called the choke price, the price that chokes off the market. So 1 point on the total revenue curve is right there. Now, likewise, demand disappears if I'm giving it away for free. What is the total revenue if my price is 0? 0. So this is another endpoint over here. And in the middle, we get a little humpy and bumpy. So this point turns out to be important. If you want to just kind of watch me and then you can draw it on your graph, come down, draw any old point, I don't really care where it is, somewhere in the middle. And then you're going to draw a parabola that goes up, maxes out, comes down, one big pile of cash. Looks like that. So this is total revenue. That's what the total revenue function looks like in its relationship to the demand curve. So total revenue is maximized when the elasticity of demand is equal to 1. That's one of our connections. Now, a more important connection, though, why this is one of my favorite graphs here, is if I take points A to points B, right? I go from A to B, and I cut my price by some amount. You know, just for fun, I guess let's do our $12 and $10 here. 12 and 10. Just for fun. My 12 was connected with 100 units. My 10 was connected with 140, right? Points A and B are directly connected with points A prime and B prime downstairs. Because they line up vertically, this is kind of cool. We go 100 down here, and this is, let's call it point A prime. And point B prime ends up being here. So let's see if it worked, first of all. If you got your calculators out here, I think I can handle this one. Point A prime, what is the total revenue at point A on the demand curve? 1,200, right? Price times quantity, 12 times 100 is 1,200. So I got $1,200 worth of total revenue associated with point A. With point B, how much do I got? 1,400. So it worked. It worked. Because demand was elastic, we had this situation going on, and we climbed up the revenue mountain to here. So a price decrease led to an increase in money in the cash register, an increase in total revenue. If I take that same $2 price change, and we're not going to calculate the numbers for this, but let me just drop down to, just for fun, let's say 5. And I cut my price to 3. I would be moving from point C to point D. Point C and point D correspond on the revenue mountain with C prime and D prime. And as I heard somebody say, we're losing revenue. We're losing money in terms of total revenue for the same cut in price. So when the CEO of Pepsi asked us, would it be a good idea to do a $2 price change? The answer is, it depends on whether demand is elastic or inelastic. And that's why we have these numbers, right? Because it's showing our connectivity for our profit equation of what's going to happen to revenues. So there's a whole, this is honestly one of my favorite graphs in economics. So I think you should know it because you'll be able to answer a whole bunch of questions. So a multiple choice question might work like this, or just a short answer question for that matter. Just to give you a little feel for this. If demand is relatively inelastic, and there is an increase in price, what effect will there be on total revenue? Now, if I actually threw numbers in, one way would be to go back to your formulas and calculate all the numbers and figure out that, oh, it moves from 1,200 to 1,400 or whatever, and therefore it goes down. Like, that would probably cost you about 10 minutes. If you have this picture memorized, you've got the answer like that. If demand is relatively inelastic, we're in this range, and there's an increase in price, what happens to total revenue? It goes up. All right, so you're done. There's an increase in total revenue. All right, so all I did was I moved from D to C this time. If I have this picture memorized, these always correspond moving the same direction. Total revenues go up, total revenues go down. Sometimes we might see a question of, suppose there's a decrease in price and total revenue falls. What's true about the elasticity of demand? That'd be a flip way of doing it, right? So it's inelastic, right? So you can kind of pick apart those different moving parts. So kind of a picture's worth 1,000 words, a picture's worth 1,000 different ways of orienting a problem, if you got that connection down. Okay, comments, questions there? All right. So we've got hopefully the price elasticity of demand. This is the own price. So if again this is the quantity of Pepsi, this is the price of Pepsi. But now that you guys got the mechanics down, we can calculate an elasticity for just about anything. In other words, what's going to be the effect of Pepsi if Coke prices go up? Suppose Coke raises their price by 10%. What's going to happen to the quantity of Pepsi? We can calculate that. Which direction, first of all? If there's an increase in the price of Coke, what happens to the quantity of Pepsi? Goes up, right? Complements or substitutes? Substitutes, right? So chapter 3, that was a demand shifter. We used the supply and demand curve to show a shift. Now we're going to use the elasticities to quantify that in the same way we just did the price elasticity. So we call that a cross-price elasticity. So the cross-price elasticity, which I'm going to put a little sigma subscript CP for cross price. Okay, hang on tight here. Here we go. Brand new formula that you got to have memorized. Now, if I stop there, does that look kind of similar? Same thing. You're not really memorizing a new formula, right? But what we're going to do now is that this is, let's say, Pepsi, and this is, of course, Coke. Generically, if we were trying to not be fun, we could put price of good 1 and the quantity of good 2 or something like that, right? So we're just talking about quantities of one good versus the related good or potential relationship of the good. All right, the rest of all the business follows the same way. So we still have the averages. This is just put equals same way as the elasticity of demand. Percentage change in quantity is the quantity divided by the average quantities. The change in Coke, new Coke price minus the old Coke price divided by the average Coke price, all of that's the same. Okay, so you just kind of work through the details in the same fashion. So with this one, let me do a little bit of a example. Let's see here. I could make one up. Okay. So, formula, or interpretation, or definition, sorry. Definition. The cross-price elasticity is a number, unitless number if you wanted to write that in, a number that shows the responsiveness of quantity demanded to a given change in the price of a related good. A number that shows the responsiveness of quantity demanded to a given change in the price of a related good. So example. Suppose beer prices fall by 10% and sales of wine increase 12%. What is the cross-price elasticity of wine?
Excuse me.
Some numbers? What, you got a question? Was that you, Davis? Or Tyler?
No, Tyler. Can you write that equation closer to this side so I can see it?
Yes. Elasticity cross price equals percentage change in quantity demanded divided by the percentage change in the price of the related good. So what I did up over there is I put Pepsi and Coke.
Thank you.
So one bad part I have, I usually have the camera out here somewhere. Numbers? What do you got? 1? 1.2. 1.2? Anything else? I haven't heard the right answer yet. So I was hoping that there was other answers. Negative 1.2. Can they be negative? So the elasticity cross price of wine equals the percentage change in the quantity of wine divided by the percentage change in the price of our beer. So wine sales do what? Increase positive 12%. Beer sales do what? Decrease 10%. We get a negative 1.2. But these things are always positive, right? Absolute value, take the absolute value. Are beer and wine substitutes or complements? Substitutes? So let's see what's happening here. A decrease in the price of beer leads to a increase in the price of wine, or increase in the quantity of wine, sorry. So are those substitutes or complements? A decrease in the price of jelly leads to an increase in the quantity of peanut butter. They're complements, aren't they? If it's a negative sign?
Yeah.
So were you in your mind kind of thinking, oh, everybody knows beer and wine are substitutes? Got to be able to interpret the numbers, the data here.
So if it's negative, it's always a compliment.
If it's negative, it's always a, is it a complement or substitute? As the price of Pepsi goes up, the quantity of Coke goes down. As the price of Pepsi goes up, Coke sales go up. So that's a positive relationship for those two substitutes or complements? Substitutes. Positive means they're substitutes. Negative means they're complements. All right, now I wanted to bring this up because sometimes results, part of the reason we do economic analysis like this and study elasticities is that they're counterintuitive. Like, we crank out the numbers, we kind of think, oh, everybody knows beer and wine are substitutes, and yet we get this answer. When we actually collect real-world data and analyze beer and wine numbers, we get something that maybe is not quite what we were expecting. And so, is there a story there that would make them complements? I don't know, if you're having a party, if it's a Saturday, if it's a Saturday and you're having a party, are you just going to stock only beer or only wine? Or maybe because you're having a party and it's a big party and a lot of people coming, you might carry both. The two are complements if you're throwing a big party, right? So don't necessarily let that steer you one way or the other. That's part of the reason that we calculate out the numbers. All right, so interpretation. Interpret. The numbers equal 1.2. What's a convenient way to learn the interpretation? Put it over 1. Any number can be put over 1. And now we let this thing read itself. This 1 corresponds with the downstairs of the formula. This 1.2 negative corresponds with the upstairs. And so the interpretation becomes a 1% increase in the price of beer will lead to a 1.2% decrease because of the negative sign in wine sold or sales. So there's our nice little interpretation. With cross-price elasticities, the sign matters. A negative sign means these two goods are complements. A positive sign would mean substitutes. So the summary would look something like this. If the cross-price elasticity of demand is less than 0, negative, if you get a negative number, then the goods are complements. The goods are complements in production, or in consumption rather. If the cross-price elasticity is greater than 0, the goods are substitutes in consumption. So remember, this is kind of fancy math notation of just saying if that number turns out to be negative. The case we didn't cover is what if it's equal to 0? What if you do all the numbers, you collect some data, and you crank out the numbers, and the cross price elasticity is equal to 0? What does it tell you about the two goods? They're unrelated. Yeah, there's no relationship between the two. So then the goods are unrelated. There is no relationship between the two that we can pick up on anyway.
At what point would the increase of beer be to the point of where wine sales go up then? Because there's going to be a point where the people who were buying beer are going to go over and start buying wine.
Similar to the elasticity of demand, depending on the volume of sales and the price changes, these numbers will change.
And then the
elasticity would change.
Not complement into.
Possibly, or they'll just become unrelated and nobody cares if the price. It's the responsiveness of the two that we're honing in on. All right, we'll call it a day there. Good work, people. That was pretty heavy. So by the way, we got through about 3/4 of chapter 4. I'm going to come back and talk about income elasticities, and then we'll get into chapter 5. So, Lego movie. Hopefully everybody got my email. Right? Extra credit tomorrow night. If you bring a friend, you get double extra credit. A friend that's not in this class. That's fine. Yeah, as long as you come as promptly as possible. Yeah, I mean, if you drift in at 9:30 or something, and this looks yeah, absolutely. Yeah, those of you who haven't made it past the math quiz, come on up. Oh, this is what your question was.
Yeah, we have a team score of 1.29.
Percentage or
Out of 20.
is it a percentage though?
Well, I mean, it's like, it's a very.
Why don't you pull yours up? Let me just take a look at it. Okay, let me close that. Get into Firefox. Let me close this off.